do not put anything in the chart in the chat. If you don't want to be anything that you don't want to be recorded, don't put them in the chat as well. So, Mo, maybe you can start recording now.
Okay.
Well, good afternoon. Welcome to the short course, the NOAA Environmental Satellite Enterprise Application Opportunities. The satellite application virtual training for students that are organized by the MS Satellite Meteorology, Oceanography, and the Climatology Committee called SATMAC Committee. The SATMAC Committee actually has worked probably in the last half year, almost every 2 weeks, the organization committee will meet and discuss the plan, invite speakers, coordinate the logistics, and to provide actually real free training session for you to participate and enjoy. These training sessions are designed as an opportunity for our students during the summertime to learn new and interesting satellite applications enabled by research activities and new satellite data products conducted by the NOAA and other federal labs or university labs. They are meant not to be in any textbooks. So what you are going to learn is actually something very new, very fresh. It also provides opportunity for who are changing their careers or moving to a position that requires increased knowledge about environmental satellite remote sensing. So my name is Jun Wang. I'm a professor in the College of Engineering in the University of Iowa. I'm one of the AMS SATMAC organization committee members for this event. Joining me here also, there are many other members here that we may provide them the list of their names in the chat. So today is actually the second of our 4 sessions we plan for this summer. This session will be led by Dr. Jeff Key and Dr. Yinghui Liu, both from the Advanced Satellite Product branch in Center for Satellite Application and Research, STAR, in NOAA NESTIS. So Dr. Jeff Key is the chief of the Advanced Satellite Product branch in the Center for Satellite Application and Research in NOAA, based in University of Wisconsin-Madison. And his research focused on developing innovative methods to observe polar regions from space, improving our understanding of polar climate and expanding cross-spherical observations internationally. Jeff has served on many international committees and currently leads the Cryosphere and the Polar Observations team as a part of the World Meteorological Organization Global Cryosphere Watch program. Dr. Yinghui Liu is also a scientist who studies the Cryosphere in the same division with Jeff. And his current work focuses on developing operational satellite snow and ice products and their validation, calibration, and application. He's also interested in the atmospheric cloud, sea ice, and ocean interaction in the polar regions. So we're going to be a very informative session that talking about the basically remote sensing of snow, ice, sea ice in the Cryosphere. So very exciting opportunities for our students. So with that, Jeff and Yinghui, you take away from here.
Okay, thank you very much, Jun. I appreciate the nice introductions of myself and Yinghui. I'd also like to introduce Kyle Obremski. He's online somewhere. You probably don't see him. I don't think his camera is on. Kyle, can you turn on your camera?
Just turned it on. All right.
There you are. Okay.
Yeah.
So Kyle is a graduate student in the Department of Atmospheric and Oceanic Sciences here at the University of Wisconsin-Madison, and he's therefore also a graduate student in our Cooperative Institute for Meteorological Satellite Studies, SIMS. He contributed to this presentation, the second part, the hands-on part. I'll get to that. And we'll be working on the same topic more quantitatively than we will be doing here today for his master's thesis. And also we have Scott Lindstrom, who is a scientist here in SIMS and the Space Science and Engineering Center. Scott, if you're on, can you show yourself even briefly?
I've turned on my camera.
Okay, thank you. And Scott will be leading one of the breakout groups. Kyle will be leading one, and both Yingwei and I will be leading two others. So, and I think it'll be just about right. We're at 35 participants now. Maybe we get to 40. With 4 breakout groups, we'll probably have 10 in each. We'll all be working on the same problem. We'll say more about that later. So what you should all be seeing is the agenda. I wanted to just give you an overview of what we're going to do here for the next almost 2 hours, 1 hour and 55 minutes. And the goal ultimately is we want to understand enough about our JPSS and other satellite products to be able to look at the opening of the Northwest Passage, the navigation route through the Canadian Arctic archipelago. And that was a big deal back in 2016 when a cruise ship did traverse the Northwest Passage. We're going to look at that year and another year where it was not open. And then we're going to do that all together. Yingwei will lead that. And then after that, in the breakout sessions, we will have 2 other years where we'll look at the same types of satellite data and try and predict, or at least determine ahead of time, whether or not the Northwest Passage is open in each of those years. So very exciting, a lot of fun. We'll keep it relatively qualitative, just looking at figures, and hopefully you'll all enjoy it. So that's the overview, but just the timing of it all before we get to that fun exercise, which will take about 1 hour and 15 minutes collectively. I wanted to just talk a little bit about the just remote sensing of the cryosphere, not just JPSS products, but all different types of products, different types of satellite instruments for remote sensing of the cryosphere. So I'll spend, well, I have about 23 minutes left, so that's how long I'll spend on it. I have a few questions sprinkled in where we would ask you to just type a response in the chat if you have an answer to the question, and that will also continue into the next session as well. Then the hands-on activity, like I said, Yingwei Liu will lead that, as well as Kyle Obremski will present the first part of that. Then that'll be about 45 minutes of working through a case study. Lots of fun. Pay attention to that, because then when we go to the breakout groups for about a half hour, you'll be working on doing the same kind of thing, but like I said before, with 2 different years. Then we come back to the whole group and wrap things up. So that's where we're at right now. I put a link, and I'm going to do it one more time, to all the presentation materials. You'll see another link later on that has these same materials, but also some nice video, a few videos and pictures of sea ice. We're really focusing on sea ice for this activity, but we'll come back to that. So hopefully the 34 people here can access all the training materials. I encourage you to download them, especially when we get to the breakout group, because you might want to flip back and forth between figures just on your own, rather than what we're showing the whole entire breakout group. Okay, so I'm going to switch to my presentation and then proceed through it. Again, this part of it is not focused on the Northwest Passage, but rather remote sensing of the cryosphere in general. I wanted to give that background before we get to actually using JPSS products in particular. So first, what's the cryosphere? I've said the cryosphere many times. Some of you maybe are cryosphere people, snow and ice people. Others may not. And when you hear cryosphere, maybe you're thinking about frozen human bodies out in space sent off to another planet. But that's not what we're talking about here. We're talking about snow and ice, really the water in its frozen state. Generally, we're referring to the surface. Now, if I wanted to get picky, some people that work with permafrost would say you can have cryosphere without the water, but we won't get into that. Just think of it as water in its frozen state, solid precipitation. Well, I said at the surface, and here I'm talking about atmosphere, snow cover, sea ice, lake ice, glaciers, ice caps, ice sheets, ice shelves, permafrost, and seasonally frozen ground. Now, what's important about the cryosphere, or one thing that's important, is that it's not just a very high latitude phenomenon. It is, in fact, global. Some parts of the cryosphere occurring in about 100 countries across the globe. So, and that's a very crude illustration or map of where the cryosphere does exist. It is at all latitudes, although you think in the tropical regions, it's going to have to be at high altitudes, high elevations, and that would be snow cover as well as glaciers. So let me ask you, all of the participants, what are some of the impacts of a changing cryosphere? I'm going to give you about 30 seconds to type it in the chat. Anybody and everybody can type. If the cryosphere is changing, name an impact or two or three. Anything. Increased floods, thank you. More water, oh wow, here we go. Sea level rise, ocean currents, shipping channels, sea level, all excellent responses. Albedo, interesting comment there on changing albedo. Absolutely true. Salinity changes in the ocean. Very, very good. Okay, keep them coming, but now let's go on and just look broadly at some of the impacts. This is more in terms of societal benefits, impacts to shipping, which somebody mentioned in a different word, fisheries. I didn't see anything about fisheries. Coastal erosion from a melting permafrost is really a big deal, and you see that in the bottom right picture here on this slide. Weather, glacier collapse, okay, that feeds back into sea level rise, but also to land hydrology and water supplies, right? And floods. Somebody else had mentioned floods. So excellent suggestions in the chat. Thank you for doing that. Also, changes in snow cover impact water supply as well as glaciers that we just mentioned. Agriculture can be impacted tremendously by changes in water supply by alpine snowpack, for example. Infrastructure, you see a picture of railroad tracks deformed in the lower left there from melting permafrost. And we had a number of people mention sea level rise, change in fauna composition. Yeah, okay, ecosystems, both land and ocean ecosystems. Tectonic plate changes, I suppose because of gravity changes. That's one I hadn't thought of, but yeah, and many feedbacks within the climate system, which comes back to somebody mentioning albedo as well. Okay, thank you for the input. So how does the Arctic look from space? We're focusing on the Arctic. I'm talking about the cryosphere, but for the hands-on, we're looking at the Northwest Passage, which is in the Arctic. We'll show some maps of that later. Yeah, this is one of my favorite questions. Another one for you. How are the Arctic and Antarctic different? Put your answers in the chat. Anything. Antarctic is a continent, exactly. Yeah, that basically says it, north and south. Okay, yeah, that's good. That's true. Arctic is in the northern hemisphere, Antarctic is in southern hemisphere. But let's go back to the Antarctic is a continent. That was the main thing that I was looking for. Yeah, ocean currents around the Antarctic do separate it. That's actually an excellent point, because that has a big impact. It's not just ocean circulation, but also atmospheric circulation does cut off the Antarctic from exchange of energy and mass from the mid latitudes. So that was an excellent point. And yes, what Evan White just said, Arctic is mostly sea ice while the Antarctic is mostly land ice. Yes. And to put that all together, the Arctic is an ocean surrounded by land. The Antarctic is land surrounded by ocean is really all I was looking for, but great responses. So moving on. Just some pictures of the Arctic from space, from different instruments. I think this is probably from the VIIRS instrument on the JPSS satellites. Could be MODIS, actually. I don't know. I should know that, but I don't. It's one or the other. So a high resolution optical instrument, but in this case, a bit lower resolution to show the entire Arctic. Here zoomed in with a very high resolution instrument to show some characteristics of sea ice, where you can see the ice flows, the water and thinner ice in between the flows, the ridges on the ice, and so forth. Here's a VIIRS day-night band image. So this is actually at night with under full moonlight, as it says there at the bottom. So this is showing some portion of land, but mainly for the sea ice that you see in the upper right part of the image, most upper half, but towards the right, and so forth. Glaciers, okay, it's not sea ice, but we do want to look at glaciers. So high resolution instruments like Landsat, for example, give us a lot of information on glacier movement, glacier shape, not so much volume, but that comes with an altimeter as well. We do here have these composites, 3-hourly or even hourly composites of multiple satellites, geostationary and polar orbiting. So you get a nice view of changes in cloud cover, for example, but you can also see, if you zoomed in, sea ice motion. Active and passive microwaves see through the clouds. So that's probably active and passive microwave, active meaning radar, synthetic aperture radar, have the longest records, passive in particular, of sea ice cover of all instruments. And the record is very good starting in the late 1970s. Radar is a little more spotty because it tends to be higher resolution and usually just with special acquisitions, but we're getting more and more radar data as we go along. Gravity is one thing that gravity sensors that people don't typically think of in terms of the cryosphere, except for those who use gravity for studying ice sheet mass and mass balance. And so the change in the mass of the ice sheets has an effect on gravity, and that can be detected with instruments like or satellites like GRACE. So we take a lot of this raw data, we turn it into products. That's what we do here and in NOAA and in our part of NOAA. And here's an example of both snow and ice cover, just binary, where the snow is, where the ice is, and how it's changing over the course of the year. Ice sheet elevation, I think I have a question here. I didn't mention the instrument, but what kind of instruments can be used to measure elevation? If you have an idea, there you go, altimetry. Yeah, maybe that was too simple. Okay. And you can use altimeters to make digital elevation models as well. So yeah, we have different kinds of altimeters. LiDAR is one of them. So you can have a LiDAR altimeter like on ICESat. A oscillometer is actually looking up. So we use that more for clouds, at least that's my experience, but there may be other applications. But back to altimeters, you can have a laser altimeter or a LiDAR like on ICESat 2 and the original ICESat, as short-lived as it was, but also a radar altimeter that then sees through the clouds. And Cryosat 2 is probably the first and best example of a radar altimeter. And they have different, they're both used for sea ice thickness, by the way, estimating sea ice thickness, but they're viewing somewhat different parts of the ice and the snow on top of the ice. And I won't get into those details, but they're both very, very useful. In fact, this is too much to read. Don't try and absorb this. The point was we have synthetic aperture radar instruments, not NOAA, but globally, scatterometers, altimeters, gravity instruments, passive microwave instruments, visible near-infrared, thermal infrared instruments, geostationary orbits, polar orbiters, and so on and on and on and on. And we have those in the past and some that don't exist anymore and big plans for the future. And there's a lot out there for remote sensing of the cryosphere, satellite remote sensing of the cryosphere. And yes, I guess I just said that really observing the Arctic robustly, comprehensively, does require many, many satellites, not just NOAA's satellites, but also those of NASA and European Space Agency and EUMETSAT and the Indian Space Agency, Japan, JAXA and China and so forth. I can't name them all, I guess. In JPSS, we tend to focus on just the river and lake ice, sea ice, and snow cover. We don't really cover ice sheets, ice caps, glaciers, permafrost, mainly because we don't have requirements for those. We don't have people yet asking for that kind of information, particularly for numerical weather prediction. So our focus here today is on sea ice, but we do cover very robustly snow and less so river and lake ice. We have many, many products. I have to speed up a little bit. For snow cover, for not just snow cover, but also snow characteristics, particularly from AMSR 2. AMSR 2, by the way, is on a JAXA satellite, GCOM W1, but it's a partner with NOAA. So we do snow properties like depth and snow water equivalent, as well as sea ice characterization with a passive microwave instrument, and then with VIS and infrared from both JPSS VIRS and GOES-R ABI, we do similar products from those two instruments, although the spatial coverage is different. And you'll see some of these products in action after I'm done here. Some, just quickly paging through some examples of some of our products. Ice surface temperature from VIRS. We've been doing ice surface temperature from various instruments for 10, 20, 30 plus years, but with AVHR before, then MODIS, then VIRS. And we get the skin temperature or the radiating temperature of the ice. VIRS ice concentration you'll work with very closely in the hands-on exercise. Ice thickness, you'll also do some work with. We estimate ice thickness from infrared data, believe it or not. And, oh, sorry, I guess somebody has to admit this person because it messed up my, okay, there we go. Okay, a question for the chat. Who cares about ice thickness? Any ideas? Why is ice thickness important? What are the applications? Why do we want to know? Why do we want to be able to estimate ice thickness from space? Any thoughts on that? Shipping, yeah, navigation, Arctic navigation, sure. Icebreakers can plow through pretty thick ice, but if you don't have an icebreaker, you'd sure like to know how thick the ice is. Anything else? Greenhouse gas concentration. Oh, interestingly, there are questions about bromine. Volume of glaciers. Well, here we're talking about sea ice, not glacial ice. But ice, the thickness of glaciers clearly is very important. Yes, air-sea flux exchange. That's and energy, and whether it's radiative fluxes or turbulent heat fluxes and vapor fluxes. Yes, that was the other answer I was looking for. Really has a big influence on, in numerical weather prediction. Interestingly, sea ice thickness is not something that has been assimilated, mainly because we haven't had good space-based sea ice thickness products that give broad area coverage, but that's changing very quickly. And so modelers are starting to work more and more with experiment with sea ice thickness products in their numerical weather prediction. Ice concentration from AMSR2, that's a passive microwave instrument. You're going to work with that, so I'll move on. Ice motion, we're not going to work with directly, but it's another product. From both VEERS, we do it, and from AMSR2 and blended. And snow fraction, I already mentioned. This is a time series of snow fraction over Alaska. And snow depth and snow water equivalent from passive microwave. So these are snow properties that are important. I'm going to have to skip that question. We've been working on products to characterize leads. Sea ice leads are more or less linear fractures or curvilinear fractures in the sea ice. It's from stresses on the ice, generally wind induced, where you have diverging sea ice that opens up a crack. And then if it's winter, it starts to quickly refreeze. I wish we could spend more time on leads, but we can't today. But anyway, this is another product we have in a research mode at this point. We have users at the National Ice Center. These are operational ice analysts. I need to change this, not called the Alaska Ice Desk anymore. It's the Alaska Sea Ice Program. And we're working more and more with modelers on the use of our products. And I'm going to skip these slides, but they're in the presentation, and just go to the end here so we can move on. Many types of satellites. The good thing about what we're doing in NOAA now is that we are reaching out to other agencies, making partnerships to use their data, their instruments for some of our products. The partnership with JAXA is an excellent example, but we're also working with the European Space Agency using their synthetic aperture radar data, and also with EUMETSAT, another European but operational satellite center or agency. We are working together on a joint system called MEDOP second generation. We also have a NOAA instrument on the first generation of MEDOP right now, the AVHR, but we're looking to the future on that. And there are lots of applications. It's not just navigation for our products, marine navigation. It's not just snow hydrology, but also numerical weather prediction, as well as ice operations for many of our products. And we do quite a bit of work now with Arctic climate change in particular, and interactions between clouds and sea ice, for example, and feedbacks in the system. And I'll stop there. So if you have any questions, I guess put them in the chat. I don't see any. Otherwise, I will stop sharing and give Kyle Obremski and Yingwei Liu a moment to, I guess I did stop sharing, to pull up their presentations. And sorry, I lost the chat here. Okay, I don't see anything in the chat. So I think Yingwei, you were going to pull up the presentation, but Kyle's going to start off.
Yeah, I'm sharing my screen. Can you see my screen?
No,
Not just
I
yet.
don't.
Oh, here it comes.
Now it's coming.
Right.
There we go.
All
But
right.
go to slideshow mode, please. There we go.
All right. As Jeff mentioned previously, my name is Kyle Obremski. I'm a graduate student at the University of Wisconsin-Madison, working with Jeff and Yingwei. And in this part of the course, we're going to dive a little bit deeper into actually using the satellite data in the form of figures to take a closer look at the behavior of sea ice in the Northwest Passage specifically. Next slide, please. All right, so here's a kind of a roadmap of what we'll be doing. I'm going to go through some background of the Northwest Passage, and then Yingwei will take over and go through a case study and he's going to set us up for our breakout room activity. Next slide, please. Before we go any further, well, we need to understand exactly what sea ice actually is. So sea ice is formed at the sea surface by the freezing of seawater. It's a little bit different than regular water because of the salinity. So it freezes at about 28.8 degrees Fahrenheit, which is just over 3 degrees colder than normal water. So sea ice is formed and melts entirely in the ocean, which is like the big difference from sea ice compared to other forms of ice that we've discussed. Sea ice is categorized by age, thickness, and its form. In terms of age, sea ice is most commonly divided into first year and multi-year ice. Multi-year ice is defined as something that survived one or more melt seasons. There are other age thickness categories that are listed here: new ice, nihilus, gray, gray-white, thin first year, medium first year, and thick first year. In parentheses is their thickness range. Fragile ice is the first stage of sea ice growth, where crystals or plates of ice are suspended in the water. Then we have grease ice, is fragile ice that has coagulated to form kind of like a greasy or soupy layer on top of the surface, with distinct ice flows. So other ice forms include pack ice, flows, pancake ice, drift ice, fast ice, and so sea ice is characterized by unique features often found on the ice too. So we have like melt ponds are a common response to summer melting of the sea ice surface. Warm temperatures also contribute to the form of plinii, or plinia in the singular, which are nonlinear shaped openings in sea ice that may be open water or covered with new thin ice. Jeff mentioned leads, of course, which are wind-driven fractures in the ice essentially. Pressure contributes to the formation, and ridges and hummocks. Ridges form when sea ice is haphazardly piled one piece over another, and hummocks are ridges that have been smoothed by melting and other forms of erosion. Ice shelves are floating parts of glaciers and ice sheets. When portions of glaciers and ice sheets and ice shelves break off and float away, they are icebergs. Neither are considered sea ice, though. Sea ice should never be referred to as an ice sheet. Expanses of sea ice are referred to as pack ice. Next slide, please. All right, so here are just a few images of sea ice for your reference. As you can see, it comes in many shapes and sizes. Sometimes it doesn't even look like sea ice. On the bottom left image, that just looks like tundra, but these are sea ice and it can be various thicknesses. Next slide, please. All right, so on this slide, there's actually 7 pictures. They're labeled 1 through 7 on the upper left side of each image. So some of these pictures actually show sea ice, while others show something different. In the chat, if you wouldn't mind saying which numbered images you believe are sea ice. I'll give you about 30 seconds to answer, and then we can reveal which ones are actually sea ice. Seeing some answers coming through. Yes, I should clarify, there is more than one example. I'll give you a few more seconds. All right, Yingwei, can you reveal the answer, please? Oh, is it popping up? All right, it's popping up. All right. So the pictures on the right side of your screen actually do not show sea ice, which means, yes, they did land a plane on sea ice, which is pretty astounding, which really speaks to how thick sea ice can get and how sturdy it can be. Image 2 shows a boat, actually. I know it's kind of hard with the perspective, but hopefully that's an icebreaker. That would be a little bit worrisome if it wasn't. So it's, yeah. Sea ice comes in many shapes and sizes. The stuff on the right, you have ice shelves, there's an iceberg. Image 7 is not sea ice, but yeah. Next slide, please.
Can I add something there, Kyle?
Yep.
Yeah. So in the lower left of that slide, it mentioned take a couple minutes to look at some video pictures there. Now the participants can't click on Kyle's slide there. So what I'm going to do is I put that link in the chat, and there are some really nice videos of the icebreakers, I think in Antarctica, plowing through the ice. So, you don't need to do it now, but sometime have a look at those, and you'll get some nice, a nice sense of how thick the ice gets and what it's like to plow through it in an icebreaker. So, and there are some pictures as well, by the way, as all of the same materials that you're seeing here are also on this web page. So yeah, it's in the chat.
And then could we get the next slide? All right, thank you. So like speaking of boats, going off of what Jeff said, so in 2016, there was actually a cruise ship called the Crystal Serenity that spent 32 days sailing through the Arctic, specifically through the Northwest Passage. It had about 1,000 people on board. It was an 820-foot long ship and weighed about 68,870 gross tons, with 544 cabins and a maximum capacity of 1,070 passengers. If you're interested in room prices, they started at 20,000 and went up to about 120,000. Hopefully that's for the whole trip and not per night, because that would be a little expensive. The locations the ship traveled through and stopped at are listed in that image below and in that block of text. So as you can see, the ship started in southern Alaska, actually went west and then north and then east again through the Northwest Passage, going around Alaska through the Northwest Passage, stopped in Greenland, and then actually sailed south to New York again. This was a significant journey because it marked one of the few times a non-icebreaker rated ship was able to traverse the Northwest Passage due to there being less sea ice. And, as a cruise ship carrying about 1,000 or more than 1,000 passengers, you got to be pretty confident that you're able to make it through the Northwest Passage. So that's what made that pretty interesting. I think the next slide shows the Northwest Passage actually, which will be, So this is the Northwest Passage. This is what we're going to be focusing on for the hands-on activity and pretty much throughout the rest of the presentation. It runs mostly through waters that are part of northern Canada. Can you go to the next slide, please? I think it shows the routes. Yeah. So this is another image that I think does a great job of showing the routes and the sub-routes of the Northwest Passage. When most people hear the term Northwest Passage, they think it is like one straight channel. Not everyone's as familiar with it, so they think it's one route. But in reality, it's actually a conglomerate of all these smaller waterways that are shown in the image. And you can see that they're labeled. There's 3A, 3B, so there's some sub-routes in there as well. And could we go to the next slide, please? So the importance of the Northwest Passage. I should also mention Northwest Passage is abbreviated as NWP. I know a lot of people are familiar with NWP is an acronym for numerical weather prediction, but today it's the Northwest Passage for this presentation. So sorry for the confusion. So Northwest Passage is an important climate signal. The passage is becoming passable by non-ice-breaking ships, which really wasn't the case more than about 20 years ago. And that signals a decline in the sea ice strength in the region. The Arctic in general is losing a lot of sea ice, and the decline in ice that we are seeing in the Northwest Passage is just a testament to that. As well as a climate signal, the passage has an importance to a trade route. I know earlier one of the questions people were saying shipping is an important sea ice and sea ice thickness. And I think many of us have heard about explorers in the past searching for a Northwest Passage. And the main reason for that is trade. Economically, the Northwest Passage would provide an alternate trade route that would save time and money compared to some of the shipping lanes that are mostly used today. The passage also is located mostly in Canadian waters. So it's kind of interesting, but there's some disagreement about whether parts of the passage are actually in international waters or just Canadian waters. So that's kind of setting up a geopolitical conversation that's probably going to heat up in the coming years with Northwest Passage opening more and more with less sea ice. And finally, kind of going off, this is more economics too, and the tourism industry really stands to benefit. I talked about the Crystal Serenity, but there are already cruise ships that go around Antarctica or to Antarctica. There are already Arctic cruise ships. So I think it's only natural to assume that there's going to be cruise ships or more cruise ships in the future going through the Northwest Passage. I think we talk more about the economic impact on the next slide. So just touching up a little bit more, the Northwest Passage could replace some well-known trade routes. This study by Samanthan and Zemansky in 2006 concluded that some routes through the Panama Canal could be replaced by the Northwest Passage completely because it would save time and money. I believe the major route they looked at was from Yokohama, Japan, to New York, actually. So as mentioned, the opening of the Northwest Passage will most likely set up some geopolitical tensions as Canada claims territory, but other countries, in an attempt to avoid paying trade fees, are saying that the passage does go through international waters. Whether this is true, I don't necessarily know, but maybe some of you are geographers and or cartographers and can, let us know in the chat or in the breakout session, are these waters actually international or are they Canadian waters? I don't know the true definition, but just know that it is debated amongst the countries right now. Then the next slide. So remote sensing the Northwest Passage is a great way to monitor the passage. I'm sure you are missing some direct measurements that are, pretty important, and they're always the most reliable if you are going out to the passage and looking at the sea ice. But sometimes it's not feasible. You were able to cover a lot more ground with less effort with a satellite instrument. The Northwest Passage covers a lot of area, and sending people out to take direct measurements, every day along the whole path of it is just not feasible. However, using spaceborne observations in tandem with direct observations is a great way to monitor the Northwest Passage moving forward, as the two methods tend to complement each other. This is going to be especially important if it becomes a more popular shipping lane. If you have tourists going out there in cruise ships, you don't want any unfortunate situations to occur. You want to make sure everyone's safe. So, monitoring the Northwest Passage is going to become extremely important in the near future. So I think that does it for me. Yingwei, are you taking over?
Sure.
Okay.
Yeah.
Thank you.
Right. Thanks, Jeff, for covering the Cryosphere and introducing the products, satellite products, and also thanks, Kel, for introducing the Northwest Passage. So in the next few slides, I will focus on a case study trying to understand the factors influencing the opening of the Northwest Passage using satellite products and also with other supplemental data like the array analysis data set. Before we go into the case study, I want to introduce the definition of the opening of the Northwest Passage. That means a ship not rated as an icebreaker can go through the Northwest Passage. That means the Northwest Passage is open. One example is the Crystal Serenity passing through the southernmost route in 2016. So on the upside is the closeness of the Northwest Passage. That means the ship cannot go through the Northwest Passage. So this is the SUMI MPP Veer's color image on August 8th, 2016. The red line shows the ship route from the Beaufort Sea south of Victoria Island, then going through the islands of Prince of Wales and Somerset, then all the way to the Baffin Bay. So this actually is the cruise route in 2016. So in this year, the Northwest Passage was open. On the other side, in 2013, this is the year, this is a true color image from MODIS. You can see the route was open south of Victoria Island. However, it was closed between the Prince of Wales Island and Somerset Island, all the way to the Baffin Bay. So in 2013, the Northwest Passage was closed. So our case study is trying to understand the factors influencing the opening of the Northwest Passage. Why in some year it was open, in some year it was closed. So these two animations just further show the ice concentration in August 2013 on the left and in August 2016 on the right. So shows the opening and the closeness in these 2 years. So the question is, in which year is the NWP open? That's obvious, or already mentioned that. But a good question is, how long did it take for the passage become open? So by looking at the animation, you can see the how many days for part of the Northwest Passage become open. So if you can write your response in the chat box, that would be good. So I want to point out the source of the Victoria Island in 2016. The product shows it was there's ice concentration there. Actually, that's the one caveat of the passive microwave ice concentration product. It has coastal contamination. Actually, it was open in this location, while the product shows some ice concentration there. So the answer to the question is, sometimes it takes only a few days for a place to become open or become as free from ice covered in just a few days. So it's that quick. So this slide just shows the governing equation for the CS thickness changes. On the left is the CS thickness change with time. I won't go into the details of all the terms. I just want to point out the term in the blue color. That's the dynamic factor of the CS growth. That's a function of the ice thickness and the velocity as motion vectors. On the another term in the red color is the thermodynamic factor of the CS growth. So that is the how the CS affected by the dynamic factor and thermodynamic factor, those two main factors. So this shows thermodynamic only CS model. So in equilibrium state, at the interface of the atmosphere and the sea ice, the conductive heat flux from the bottom of the sea ice, which is QI here, is balanced by other net heat flux terms, which includes short wave radiation, long wave radiation, and turbulent heat flux. So the QI though is the only term that is closely related to the CS growth. And also it is the function of the temperature difference between the interface of sea ice and ocean and the temperature at the interface of sea ice and atmosphere. So in this hands-on activities, we won't look at the thermodynamic CS growth model. We will look at the freezing degree days, FDD, and which is calculated as the sum of the temperature difference between the seawater freezing point and the daily average air temperature. If you recall the thermodynamic CS model, the CS growth is closely related to the QI, the conductive heat flux, which is a function of the actually the TF, the seawater freezing point, and the surface temperature. So FDD somehow is closely related to the CS growth if you look into the CS models. So if once we have the FDD, we can use two empirical equations to estimate the CS growth using FDD, which is listed here. So in summary, the FDD relates the air temperature or surface temperature with CS growth. So FDD can be used as a measure of CS growth in the growing season. So I pose the questions here. Does a larger FDD mean that CS will grow more or less in the growing season? So if you can type your response in the chat box, that will be great. I will review the answer shortly. So if you look at the FDD definition, a larger FDD, since the TF, the seawater freezing point, is constant, so a larger FDD means the air temperature or the surface temperature is lower. A lower temperature means colder, so that will favor the CS growth. So a larger FDD means that CS will grow more. So in order to look at the thermodynamic factor of the CS growth in those 2 years, 2013 and 2016, we need the daily air temperature or surface temperature. I won't show the air temperature for every day, but I will show the monthly mean air temperature and also the monthly anomalous air temperature at 2 meters, which is shows here. This is the temperature anomalies in January, which is the left column, February, the middle column, and May, the red column, in 2016 on the top and 2013 on the bottom. This is anomaly, which means the monthly mean, the difference between the monthly mean 2 meter air temperature and the climatology mean. So a positive value means a warmer monthly mean air temperature, and a negative value means the colder monthly mean air temperature. So you can see in 2016, the air temperature is warmer than the climatology mean, which means a warmer January, February, and May in 2016, and a relatively colder air temperature in 2013 in January, February, and May in 2013. So that's just the instantaneous air temperature. So to look at the accumulated effect, like the accumulated over a month, 2 months, or 3 months, we need the FDD. So this two figures shows the FDD on the last day of March in 2016 on the left, and last day of March in 2016 on the right. So if you look carefully or more closely, you can see the FDD values in 2013 is larger than that in 2016. So the question is, which year is colder based on the FDD? So I think the answer is obvious. The larger FDD means the colder air temperature, accumulated air temperature, and which also favors the S growth in that time period. So I already answered the question. So 2013 is colder and 2016 is warmer. And the colder temperature, air temperature favors the CS growth over the Northwest Passage area. And 2016 is warmer, that less favors the CS growth over the Northwest Passage. These two figures just to further confirm that this is the FDD anomaly on the last day of March in 2013 on the left, and March in 2016 on the right. So I already said the positive values and also the positive anomalies means colder temperature, air temperature, and the on the left, and the negative values means the warmer air temperature, so on the right. So the cold air temperature favors the CS growth. So we want to look at does that have any impact on the ice concentration in March 2013? So by looking at the ice concentration in 2013 on the left and in March 2016 on the right, we see almost exactly the same CS concentration distribution. So we don't see any difference. So the question is, does March ice concentration seem like a good indicator of the NWP ice concentrations in the summer? To confirm that, we look at ice concentration anomalies in March 2013 on the left and in March 2016 on the right. They are exactly the same, almost exactly the same. So it appears to us the ice concentration in March might not be a good indicator of the NWP ice conditions in the summer. So already mentioned, the cold air temperature favors the CS growth, and warmer air temperature less favors the CS growth. Why does not impact reflected on the CS concentration? With that question, we look at the CS thickness. So these two figures shows the ice thickness anomalies in March 2013 on the left and in March 2016 on the right. So the red color means the CS thickness is larger than the climatology mean, and the blue color shows the ice thickness is lower, smaller than the climatology mean. And the more darker of the blue color means smaller or the CS thickness. You can see if you concentrate on the Northwest Passage, you can see the darker blue color in 2016. That means the CS thickness actually is much smaller than the climatology mean. So this tells us the warmer or the colder air temperature favors the CS growth, and the warmer temperature less favors the CS growth. So by the end of the March, the warmer temperature in 2016 grows the CS lies in the winter of 2016. So that shows in the ice thickness much smaller than the climatology mean. So it means in 2016 winter, the CS grows less. So even though the ice concentration does not show any difference, because in March, that's the maximum CS extent in the Arctic. So, but however, that warmer air temperature in 2016 is reflected in the CS thickness field, resulting in much less CS growth in that winter. So the question is, does March ice thickness seem like a good indicator of NWP ice concentrations in the summer? So our observations, yes, that might be a good indicator of the NWP ice conditions in the summer. So then we also look at the freezing degree days at the end of May of 2013 and 2016. So this is FDD on the last day of May in 2013 on the left, last day of May in 2016 on the right. So these anomalies, and we also look at ice concentration anomalies, and also the ice thickness anomalies. Basically, it tells a similar story as we look at the FDD and all the anomalies by the end of March. That means the warmer air temperature less favors the CS growth, CS less in 2016, leading to a thinner CS by the end of May, and goes on. So also we look at FDD anomalies on last day of July in 2013 on left, and in 2016 on the right. So these two figures also tell us by the end of July, it's the accumulated air temperature is colder in 2013 and warmer in 2016 over the NWP area. So I think the question is, with the FDD anomaly patterns in 2013 and 2016, which year would you expect the Northwestern Passage is more likely to be open? I'll pause for like 20 seconds for the answer, for the response in the chat box. So our observation is the thermodynamic factor, primarily temperature, either a surface temperature or air temperature, certainly favors CS growth in the Northwestern Passage in 2013. So the Northwest Passage is more likely to be open in 2016 than in 2013. Now let's examine the dynamics factor. If you recall the equation, there is a thermodynamic factor term. There is also the dynamic factor term. The dynamic factor term is a function of the CS thickness and the ice motion vectors, either come from the wind-induced ice motion or from the ocean currents induced ice motion. To further look at the dynamic factor, let's assume two scenarios. So the background of these two figures is the same. So that's the CS thickness in January 2000. So you can see the thicker Arctic CS just north of the Canadian archipelago then becomes thinner and thinner towards the Russian side. So this is same. Let's assume on left, let's assume the wind direction is from the Canadian archipelago to the Russian side, from left to right or from the west to east. And this actually, the wind direction will favors the CS inside or in the Northwest Passage to the Arctic Ocean, basically exporting the CS from the Northwest Passage into the Arctic Ocean on the left. So I think this favors opening of the NWP. On the right side, the wind is blowing from the east to west. So that will move or pushes the thick CS, Arctic CS into the Northwest Passage. That probably does not favor the opening of NWP, especially the CS just north of the Canadian archipelago is very thick. So the question, what other wind directions might favor opening of the NWP? So I think any wind direction that moves the CS, Arctic CS, into the Northwest Passage will not favor the opening of the NWP. Any wind direction moving the CS out of NWP into the Arctic Ocean would favor the opening of the NWP. With that, so let's look at the wind anomalies from January until August in 2013 and 2016. the wind pattern. So on the left is anomalous wind pattern at 1,000 hPar from each month in 2013. On the right is the wind anomalies in 2016. So a check mark here means that the wind pattern is favoring the export from the NWP area, so which might lead to opening of the NWP. So in January, if you look at the wind pattern in 2016, it's help moving the CS in the NWP out. And in January 2013 might be help the moving the CS, the Arctic CS into the NWP. So we check the, I think the 2016 January favoring the as export from the NWP into the Arctic Ocean. So here is the wind pattern in February 2016. I think it's a tie. So March, I think the wind pattern in 2013 favor the export from the NW area in 2013. So this is April, all the way May. Starting June in 2016, the wind pattern is favoring the export of the NWCS into the Arctic Ocean. June, July, and August. So questions. So with these wind anomaly patterns in 2013 and 2016, which year would you expect the NW Northwest Passage is more likely to be open? So in the earlier months might be in the 2013 wind pattern might favoring the NWP as sea ice export into the Arctic Ocean. In the later months, June, July, and August, the 2016 wind pattern favors the export of the NWP CS into the Arctic Ocean. So our observation is overall, the dynamic factor favors CS export from the Northwest Passage in 2016. So the Northwest Passage was more likely to be open in 2016 than in 2013. So this is a summary of our analysis of the CS conditions in 2013 and 2016. So we found that in the months leading up to NWP opening, there are likely early indicators that can be used as predictors for the CS conditions in the NWP. Both thermodynamic and dynamic processes play a role in the opening of the NWP, but it's not easy to identify which is more important. So that's our analysis of the 2013 and 2016 cases. That leads to our breakout session. Jeff, you want?
Sure. Thanks, Yingwei. Yeah, before we go to the breakout sessions, our breakout groups rather, and you'll be randomly assigned. So we have now 35 participants, one person waiting, so 36. Anyway, before we do that, I'm just curious, we have a multinational group of participants here. So could we take just a few seconds and type in the chat the country you're calling from? It's probably going to be mostly USA, but I know there's a variety. So put USA or, oh, Poland. Okay, Michigan, Oregon, Canada, Arizona, Czechia, oh, Colombia, Czechia, Florida. Florida is not a country. No, I'm kidding. Oregon, and neither is Oregon or Arizona. Okay, very good. Thank you, Mexico. Good. So we're going to take a short break. We're actually about 4 minutes ahead of schedule. We'll take a 5-minute break. Don't leave just yet. Then let's see how this works. Again, you'll be randomly assigned one of 4 breakout rooms. The people, let me put up my first slide here so you can see the names again. So you should be seeing, now my screen is loading. There we go. So you'll see Yingwei Liu, I think, is leading the breakout group number 3, Kyle, number 4, myself, number 1, and Scott Lindstrom, breakout group number 2. We're all doing the same thing. And in fact, let me just say what that is right now. Don't look at the questions, just look at the purpose. We're going to do what Yingwei just worked through.
Jeff, I'm still seeing Yingwei's screen. I'm not seeing. Oh, never mind.
Okay. Okay. Might have taken a minute to load. So we're going to do a case study like what Yingwei just worked through, same kinds of figures, but for 2 different years. And there will be some questions that in an online document. We'll give you the link when we get to the breakout group sessions, and we'll be typing answers in there. Hopefully you will be typing answers in there. Not everybody needs to contribute, but I hope we get some contributions, some answers to these questions, and it could be opposing answers too. So we'll get to that in just a minute. Let's take 5 minutes. So it is now 11 past the hour. So let's go to 16 past the hour, and then we will spend 30 minutes in the session, in the breakout groups, and then come back and wrap everything up. So 5 minutes until 16 or 17 minutes past the hour. See you in 5. Probably. Yeah. Okay. Well, we're waiting for everybody to come back. Let's see how many we have back here. Most. Anyway, 31. I think we started with about 35 to 39. It fluctuated. That went fast, and that was one of the comments from a participant in breakout group number 1, that it did go fast. And we learned a lot. I think what we have here is we're going to review some of the questions, but we don't have time to go through them all. But Yingwei, do you want to show the animation of ice concentration? Because I think that one was one that really will help people determine which year was open, which year was not. I don't think it was very clear from all the figures we were looking at. I think this was a tougher case than the 2013, 2016. Anyway, Yingwei, you want to show that animation, or do you want me to show it, or what?
Sure, I can show the animation.
Okay.
Either way. So
Talk about it a little bit.
okay. Can you see my screen?
Yeah, but that's not the animation.
Okay, let's
In fact, I don't even think it's in that. Oh yeah. Oh, you're in the right file. Yeah. Okay.
let me play the animation.
I can't see your screen anymore.
Yeah, he's pulling it up a different file, I think.
Can you see the screen?
No.
No.
I can see you.
Yeah.
I'm sharing the screen.
Okay, I'll share it. I'll share it.
All right.
Okay, you can see that?
Yeah.
Yeah.
Okay, Yingwei, you talk about it, please.
So these 2 animations just show the opening of the NWP Northwest Passage in 2012. Okay, on the left, you can see the the main channel, actually, the northern part of the NWP was open in 2012, almost throughout the 2012. On the other side, in 2014, most of the channels and the streets was closed, except a small part of the southern part, like south of the Victoria Island. So that's these two animations show. So the conclusion is in 2012, the Northwest Passage was open, and in 2014, the Northwest Passage was not open.
So with that, I think that might surprise some people. But you tell me, the breakout group leads, Scott, Kyle, Yingwei, did your breakout groups come to that conclusion, or was it a mixed bag, or what?
I think the people in my breakout room, there were only 3 or 4 of them, came to this conclusion, but they acknowledged that it was harder to tell because the freezing degree days didn't really have they didn't have a great signal like they did in 2013, which I can't remember which one was open now. 2016. 2016. So there was a very clear signal in that. And it wasn't clear like that with 2012.
Yeah. Kyle, any particular conclusions from breakout group number 4?
Yeah. So first off, I think time constraint was definitely one of those ones. We didn't get too far into it, but I think my group seemed to understand pretty well what the figures were showing. But again, there was some like Scott mentioned with the freezing degree days. I think it was pretty muddled, especially compared to the previous case about which one showed an open Northwest Passage. But I'm pretty confident that my group was able to work out. I know they were working pretty hard at looking at it. I think that they were able to understand the 2012 just from what I saw in the Google Doc. The 2012 was the open year.
Yeah. Okay. Yingwei, how about breakout group number 3?
Yeah, our group also reached the conclusion it's more likely 2012 was open, 2014 was closed. But we also observed the FDD pattern is not that clear until the last couple months, like starting from June. So in the earlier months, actually, the FDD is more favoring 2014 to be open. And so that's, but the wind pattern, the dynamic factor favors the 2012 to be open, started most of the month.
Okay, what about so there with the dynamic versus thermodynamic, the winds versus the freezing degree days, what about Kyle and Scott, your groups? Did they have any strong conclusion as to which might play a larger role in the opening of the Northwest Passage, or no?
I'm not sure if they did. I certainly noticed that there was a lot more. It seemed to me in 2012, the winds were much more favorable for an open NWP. I mean, the signal seemed a bit clearer in midsummer for 2012 to be open than for 2014.
Yeah. Okay. Our group, I think it was difficult. It went back and forth. It was harder, I thought, to determine. Kyle, what about your group with regard to winds versus thermodynamics or the freezing degrees?
So we didn't quite get that far, but I think personally looking at it, in August especially, I think it's a little bit easier to see that 2012 August, you have that's kind of more anticyclonic motion, which really pushes away the ice from the Canadian Archipelago Northwest Passage area. So I would say it's pretty, if you get that far and you look through all the figures, some of the months aren't so clear. But I think when you look at the final figure in August, it looks like the ice evacuation is really favoring an open Northwest Passage.
Okay. Last question from the breakout groups. What about the month? that whether there's a tipping point or not. Is there a particular month where you actually start to see changes or in these variables that might help predict the Northwest Passage opening or closing? Could be August, could be nothing useful until August, or it could be July. Or any comments on that? Yingwei, breakout group number whatever, 3.
Yeah, our observation was based on the ice concentration anomalies. We determined that May might be the critical month. Leading up to the opening of the NWP, because in July it already became obvious the NWP might be open in 2012. So
okay, Scott.
Our group also said May, which surprised me because I didn't really see a signal in May, but someone in my group did. So
it surprised me too. Yeah, Kyle, what about your group?
So we didn't really discuss that, but now looking at the figures, I think May would be when you start to see a signal, because before that it looks like you have all that gray, you don't really see too many anomalies, and then all of a sudden in May you see you see the blue and the dark reds really show up in May, and then if you go to June or July, they pop up even more, but I would say May now looking at it.
Okay. Then we had some really good broader questions. We can't go through them. I don't know if we're going to get cut off here in less than 2 minutes or not, but just to put them up on the screen, I think, these broader questions at the bottom, I think would be fun for at least everybody to think about, but again, we don't have time to discuss them now. So we looked at freezing degree days and sea ice concentration, sea ice thickness, and surface or near surface winds, but there might be other factors. Again, I'd like to open it up for answers to that, but don't have time. What kinds of tools could be constructed? Can you imagine trying to put together some empirical or physical model to predict the opening of the Northwest Passage? And if so, how much in advance do you need the data? Well, we just talked about May as a possibility. What variables? Well, we didn't really finish that, but these are, I think, really useful questions, and questions that Kyle will have to tackle for his master's thesis. These are questions he'll have to answer. So we're going to wrap it up. Any comments from Yingwei, from Scott, from Kyle? Any final remarks?
Thanks.
Thanks.
Yeah, before you go, I just want to say on behalf of the audience, I listened to part of it, and I found that very intriguing and also very instructional, informative, insightful. I would like to invite all the audience to give a round of applause to Jeff and his team. Maybe you can also do the reactions there. So
yeah.
Okay.
Okay. Well, thanks for that comment, and thanks for the nice comments also in the chat. We had fun, and if we ever do this again, we'll make some minor adjustments. But I think the whole idea went very well, and next time you get an opportunity to go on a cruise ship through the Northwest Passage, you can predict ahead of time whether or not it will be open. So thanks, everybody.
Okay, bye.
Thank you.